Okay, good afternoon, everyone. So we're going to get started on a new unit today on optimization and gradient descent. So our motivation is that in the last unit, we saw that in order to train our binary logistic regression model, we had to solve this optimization problem here, which looks a little bit complicated, and it's too complicated to just be able to derive the answer, so that's not going to work. So we have to approach this problem more algorithmically. We have to develop some method that is capable of doing this optimization, and so that's more or less what this unit is about. But as we'll see, it's definitely possible to do this, and we'll learn the way to do it. So just as a small notational thing, rather than having B denote the intercept term and then W denote all this, W1 and so on, the slope terms, we're just going to write B as W0, and then so that our W vector will have D plus 1 entries, and that first one will multiply this one term here, and that will just make our notation easier. We can put all our parameters that we need to optimize in this W vector instead of having the W vector and the B separately. Okay, so that's just a small note. Okay, so we're going to have to talk a little bit more about gradients and get into more detail. So we've seen these pictures before back in Unit 1 and Unit 2. We talked a little bit about gradients, but now we're going to come back to it and just talk about it in more detail and learn how to compute them analytically in a little bit more detail too. So again, our objective here is to find the minimizer of some cost function J. J, could be this thing, or it could be something else. We'll see other examples of it. But we're just going to generally call that thing J in this unit. So J is going to be a function of our parameters, of course. And J just has one scalar output. J is not outputting a vector of things. It's just outputting a single scalar. Okay? So we have like a vector input, scalar output function. So we want to think about the gradient of J. The gradient of J is basically, it's going to be a vector of the same size of J that tells us the direction of maximum increase at the point W, as well as the slope, how much increase you have at that point. So in other words, if we have this picture here, the little arrows are showing the gradient. And so this arrow here is pointing away from this point. So it's showing that there's uphill movement in that direction at that point. So all these arrows are pointing away, so this is going to be a minimum, right? Because all the arrows are pointing away, going up. And then over here, we see that all the arrows are converging on this point, so that's going to be a maximum. So the arrow tells us when you're right here, this is the direction, and then the length of that arrow is showing us how steep it is at that point. Okay, so that's essentially what the gradient does. It tells you the direction of steepest ascent as well as how steep it is. So we're going to get into those details and see exactly how's the gradient defined and why exactly does it tell us the direction of maximum increase in slope. We can prove that. So one comment, or a couple comments, is that when you're at the minimizer, which is this thing we want to find, the gradient is 0. So that means that if we can find the place where the gradient is 0, that might help us find where the minimizer is. But as we'll see, it's not so easy because over here, the maximum also has 0 as its gradient, right? So there's actually different classes of points, minima, maxima, saddle points, that you can find the gradient going to 0. So, but anyway, that is still helpful. If we can find those, what they're called stationary points, if we can find a stationary point, then we can at least maybe check if it's a minima or maxima. Okay, so that's kind of one of our main motivations for looking at gradients in this unit, is that we're really interested in solving the minimization problem, but gradient gives us a way of doing that. Second, in order to compute gradients, the function has to be differentiable, has to be smooth. So that's going to be another thing. Like if you have a non-smooth function like the lasso regularization, actually gives you, it's kind of like in one dimension is just like this absolute value. That gives you a point of non-differentiability at the origin. You cannot take the gradient there. And so the kind of methods we're talking about in this unit cannot be applied to those non-differentiable problems. And so what we're talking about here is not going to work everywhere, but it's going to work for a lot of the problems we're interested in solving. So we're going to focus on this easier case. Question?
Can you get if there's a true minima and then a local minima, can you get stuck in the local minima?
Yeah, that's right. So in cases where you have multiple minima, some minima might have smaller values than others, and so depending on your algorithm, you could converge to a local minima or the global one. It depends on where you start and whether the algorithm jumps from one basin of attraction to another. So
still always try and get to the smallest, like the global minimum?
So yeah, ideally we would always be able to get to the global minimum. And yeah, so we're gonna talk about those issues more when we talk about neural networks. And in this chapter, we're gonna focus more on friendly cost functions, things like convex ones where we can rest assured that there's just kind of one class of minima that are equally good, and so we can just go down there, find them. Yeah. Okay. So we're going to assume that that we can compute these gradients in this chapter. All right. And another thing that's useful about gradients, besides being able to help us find minima, is that we can use them to linearly approximate functions, and there's a lot of value in that, as we will see. Okay, so let's start with the definition of a gradient. So we start again with a scalar valued function of one or more inputs, and those inputs could be organized as a vector. So this is a function of a vector, and then it turns out that the gradient, in that case, the gradient is this upside down triangle. The gradient of this function j at the point w is just, it's a vector of the same size as w, where what you do in each term is you just take the scalar partial derivative with respect to that corresponding entry of the vector. So, top one is dj dw1, and then all the way to the bottom dj dwd, assuming that w starts at w1 and goes to wd. So whatever the shape of w is, that's the shape of the gradient. So we can also do this with matrices. So remember that, like for multinomial logistic regression, the parameters we're optimizing are actually in a structure of a matrix. So we can take gradient with respect to a matrix, and what we get is we get a matrix, the same shape as our original matrix, and not surprisingly, like the jth row and kth column here would just be the partial derivative of j with respect to wjk. So it's it kind of follows the same rule in both of these cases. Okay, so just remember the gradient always has the same dimensions as the input. Okay, any questions so far? Okay, so let's just do a simple example. So let's say we have a function j of w, where w has two entries. It's a vector with two entries. And let's just say that it has this expression, So essentially, to compute the gradient, we just need to compute the partial derivative with respect to W1, and then we compute the partial derivative with respect to W2, and then we would just stack them into a vector. Okay, so let's see what that is. So partial derivative of this with respect to W1 is just going to be 2 times W1 plus 2 times W2 cubed. Right? So that's one element, and then we would look at the partial derivative of this with respect to W2. So this doesn't matter. We'd have 2 times W1, and then we would multiply that by 3 times W2 squared. Finally, you get this. Okay, and then once you have the components of the gradient, you just stack them together, and then you have the overall gradient vector. Okay, so pretty straightforward, I think, right? Any questions? Okay, so let's see how you do this in code. Again, it's pretty straightforward. So often, when we write code, we want to not only compute the gradient, but we actually want to compute the value of the function j as well, compute them together. And that's because typically when we use the gradient, it's also very handy to know what the value of the actual function is. So it's just easy to do both together. So here we define a function that takes in w, and then you can see we're computing j here. We're taking like the 0th element of w, the first element. We're just doing all this stuff here. And this function definitely works with vectors. So that's, oh, never mind, of course it's a vector here. All right, so then the gradient, we're just doing exactly what we said to do. We compute the 2 elements of the gradient, and then once we have them, we just pack them together in a NumPy array, and then we return both j and the gradient. And if we want to run this function, we would first need to create a w vector. Here we just choose one with values 2 and 4, just arbitrary values, and then we call our function, and it returns j and j grad, and then we can print those out, and these are the values we get. Okay, yes?
No, in cases where it's not practical to manually calculate all these derivatives, isn't there a function to calculate all the derivatives?
Yeah, it's a good question. So,
like, obviously you only have 2 derivatives here, but
yeah. So when we're going to talk a lot about this when we get to neural networks, because there we have a structure where there's so many derivatives, like maybe millions we would need to compute, and they're complicated. But what we can do in those cases is we can exploit the kind of the topology of this structure, how everything is connected, and we can use a very systematic way of taking partial derivatives it's called back propagation, and we'll develop this sort of algorithm, if you will, and that is what's actually done in hardware when you train one of these deep networks, is you let the computations guide you through that. Once you have a very systematic way of handling that, then yes, it's sort of like, they call it automatic differentiation. So we'll get to that, but right now we're just trying to understand the basics, and so we're coming up with simple examples that allow us to see what's going to happen. Okay, any other questions? All right, so let's move on to a slightly more challenging example, but it's an example which is more like what we would encounter in practice. So here we have a cost function that has this form, and so this is familiar to us because here we see like a sum over training samples. We have like targets yi, and then we have some nonlinear function of features, feature values xi, but then also some parameters a and b, which are the things we want to optimize. And actually, if you think about it, what we're doing is we're fitting an exponential model to the data. So this would be, we talked about polynomial models and linear models. This would just be an exponential model where we can change the linear scaling and then the scaling in the exponential to try to match these features to these targets. Right? So it's just one of many, many things you can imagine doing in machine learning. And so now our objective is to find the A's and the B's so that we can best predict Y based on this exponential model involving X. So in order to do this, we essentially need to look at the gradient of J with respect to the parameters in W, so partial derivative with respect to A. And so we would need to use the chain rule here. So we can move our derivative through the 1/2 through the sum, and then we have to apply, we take d dA of this. So using the chain rule, we get 2 times this stuff here times the derivative of this inside stuff with respect to A. So for that, the yi goes away, you get minus e to the power minus bx, or bxi. Okay, so that's just, we applied chain rule to compute this. Is everybody good with that? Okay, and then we need to do this again for the second parameter, b, and in this case, we apply chain rule again. The only thing that changes is when we take the partial derivative of this inside stuff. So in that case, we get this expression, basically leveraging the fact that the partial derivative of this exponential is just itself times, again using the chain rule, the partial derivative of this argument, which is going to be minus xi. So chain rule is something we're going to be using a lot for the rest of the term, so it's just something to get familiar with and practiced with. So anyway, these are the two partial derivatives, and then we stack them together to get the gradient. And you can see they both depend on all of our training data. Okay. Any questions on anything on the left side of the page? Okay. So when we code this, we want to be as efficient as possible. So for example, notice that this term is present in both of our gradient components. So we don't want to recompute that twice if we don't have to. So we want to define intermediate variables where we can do the computation once and then reuse that computation later. So let's see what happens in this function. So the first thing we do is we unpack that vector into the A's and the B's. And this is really just so the code is a little bit more readable. Then first of all, again, we're going to compute both J and its gradient. So in terms of computing J, we're going to first compute what's inside this quadratic, just because you can imagine that is something we might use over and over. So let's call this y error. That's like the error between y and our prediction. And in this case, what you'll notice is that, so here, this is written as a sum over the individual terms yi and xi. So here, y and x are going to be vectors containing all our training samples. So we can use basically Python's ability to do computation on vectors by doing like y the vector minus this other vector. So when it does this exponent, it's actually doing this. It's smart enough to know that, okay, b is a scalar, x is a vector, so we can do that. And then when it takes this exponential, it's taking that exponential element-wise in that vector. And it's returning us a whole vector of these terms here. And then it's multiplying them by a and so on. Okay, so that's, so NumPy has the ability to be smart with processing of vectors and matrices and stuff this way. Okay, so once we have that y error as a vector, we can do y error star star 2. That basically takes each element, squares each element, and then we do NumPy sum to do this sum. We get back to a scalar and we multiply that by 0.5. So that's how we got our cost. Okay, any questions on this first part? Okay, and second part, now that we have this y error computed, we can use it, let's say for this term. So you can see we have y error times this other stuff. So here's our y error, and here's the other stuff. So again, when it's doing this multiplication, it's going to be doing an element-wise multiplication between every term in y air and every term coming out of this operation. So it's different than MATLAB. MATLAB, you would need a dot star for this, whereas in Python, it just assumes element-wise unless you tell it otherwise, whereas in MATLAB, it assumes matrix multiply unless you tell it otherwise. Okay, so anyway, this gives us a vector which we can then sum and take the minus, and we get the first term in our gradient. The next term is pretty similar. We just, as you can see, we have an extra xi there and an a there. So that we handle that with that stuff, and we get the second term. And then finally, we pack these two into a one-dimensional array, NumPy array, and that is our gradient. And we return both of these things. Okay, so in terms of just an example, what we can do is we can first declare the size. So ny, that's going to be how many samples are in our training data. We can, in this case, we're going to create random samples. Y, these are rand n means it's Gaussian. By default, zero mean unit variance. So we have y randomly drawn Gaussian values. We also have the same number of randomly drawn x values. And let's just choose an arbitrary a and b of 1 and 2. And now we can evaluate the cost and the gradient at that w based on this data. We just do that by calling our function and printing the results. And not surprisingly, the cost is very high because we have random data and arbitrarily chosen parameters that aren't going to fit the data at all. So you get these large values. So the cost is large, and also the gradient is pretty large. Yes.
So what is the gradient telling you about your original J?
So we can visualize it like this. So in this case, this would be like A and B. These are two parameters. And then the surface here is telling us the cost as a function of A and B. So, maybe there's a minimum somewhere. There may not be a maximum for that cost, or there might, who knows. And then depending on where you are, the gradient tells you which direction is pointing uphill at that point and how steep it is. So we'll get into those details in a moment, but that's the short answer to your question. It's telling you the direction of maximum increase in the slope at that point. And as you can imagine, why this is useful is because, let's say that I take a random guess and I start here and I want to find the minimum. What I could do is I could move in the negative gradient direction. I could move downhill, 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 and eventually I'll get to the bottom. And once I get to the bottom, because it's flat, I won't move anywhere because I'm just going negative slopes. Eventually, I just stop moving.
So you just calculate the gradient the whole time.
Yeah, so that's an algorithm. It's called gradient descent, and we'll talk about that. It's kind of where we're going, but that's going to be how we sort of achieve this using the gradient, is to take these negative gradient steps to get to the bottom. You could also take, if you wanted to maximize a function, you could take positive gradient steps until you get to the top. So, okay. So, all right. So any other questions about this example? Okay, good. So we also said that another nice thing you can do with gradients is you can approximate functions, and sometimes that's super useful because the original function might be really complicated and it's really hard to talk about and handle, but if you can approximate it, you can get a sense of, basically how it works, or maybe how it works in the region of some interesting parameters, and maybe that's all you need. And we'll use this several times through the chapter, but here we're going to kind of develop the idea first. So here's an example of an approximation. Here we have a nonlinear function, and if we want to take a linear approximation of it at the origin, that means we're essentially finding the line, this is our approximation, that best matches that function at that point. Okay, so that's sort of what we're doing in words. Now let's see how we can describe it in terms of the math. So we're going to start with the simplest case where our function just has a scalar input. So the scalar input is just the scalar w. The function is, again, j. Later, we'll handle more interesting cases of vectors and matrices. So you probably remember from some time back the Taylor series of a function. So basically, if I want to write the function j at an arbitrary point omega, and I want to write that in terms of what happens at some reference point, omega naught, so that's, we can think of it as a reference. So in other words, like for this example, this would be our reference point, omega naught, and then I'm saying, how do I write what happens for general w relative to what happens at 0? Well, what you do is the general function is just the height of the function at w0, which would be that height, plus the slope of the function at the reference point, which in this case would be that slope, times the deviation, the linear deviation of w from the reference point, plus another term that captures all the higher order terms in the Taylor series. So if you remember your Taylor series, if you didn't use this, you would have a quadratic term, which would be like second derivative times this squared, plus a third derivative times this cubed, and so on and so on and so on, all the way up to infinity. But what we're doing is we're saying we don't need all those details. We're going to basically stop after the linear approximation and collect all the extra stuff in one term. And we're going to denote this term with what we call big O. How many of you guys have seen this big O notation? Okay. Yeah, so big O notation is basically our way of saying all those other terms are going to behave, they're going to be sort of dominated by this quadratic term, and then there's a bunch of other details that are much less important than this quadratic behavior. And so in this case, remember that we are basically interested in what happens near the reference point. As you can see, this approximation is good near the reference point, and it's pretty bad as you get away from the reference point. We don't really care what happens far from the reference point. We want it to be good near the reference. So we're going to be focusing on the situation that this deviation is small. And so imagine that this number is less than 1. When you square it, it becomes even more less than 1, right? It becomes smaller if it's less than 1 in magnitude. And so that means that if you imagine there's like a cubic term, the cubic term is even smaller than the quadratic term. So that's why we don't even care about the cubic term. The quadratic term is kind of what we care about. All the other ones are insignificant. This is the biggest effect of all the terms we're ignoring. So that's, the big O is kind of saying, like, just pay attention to this worst case quadratic term. All the other ones are not even worth paying attention to. But, okay, what is it saying exactly? If we want to say it in words, and let's talk about this deviation just as epsilon. So this is like epsilon squared. So when you say something is order epsilon squared, it means it's at most a constant times epsilon squared when epsilon is close enough to 0. So just imagine epsilon is small, then this means at most a constant times epsilon squared. You don't know what that constant is, but there's some constant out there. Okay, if you want to actually see the full mathematical definition, it means this, which means there exists some positive numbers, c and delta, such that the function g, and this is what we're saying, if you're saying g, this function g is order epsilon squared, then you're saying the function g at epsilon is lesser equal to that c times epsilon squared, so that's your constant, for all epsilon between 0 and delta. So this is where we get the close enough to 0 part, and then this is where we get the at most a constant times. So all you're saying is there exists some c and epsilon. You don't know what they are, but they exist such that this holds, this upper bound holds. And it holds for all the epsilon in the neighborhood of 0, which means, all w in the neighborhood of the reference w naught. Okay, so any questions about this? So the main thing is just kind of to understand this means at most a constant times epsilon for a small enough epsilon. Okay, so let's see how we can use this. So this over here, I want to emphasize, this is an equality. So this is what we're saying as, this is the full nonlinear function here, and then this is again the full nonlinear function, just written in terms of a constant, a linear term, and another term that collects all the nonlinearities. But if you want to approximate it, then what you can do is you can just leave off this, and you just have the constant and the linear term. So now you have an approximation. These are not equal, but they should be close when you are near, when this term is near 0, so when W is near the reference point. So this is what we call the first order Taylor approximation of the function. And this is a useful thing. So again, on the right, this is our function, J, and then this is the first order Taylor approximation at the point 0. If we were doing the first order Taylor approximation, at the point 6, then it would be a line that would look like this. Essentially, you want right at that point, it should match the original function in height and in slope. But beyond that, it's linear, it's a line. So there's no other matching of the higher order derivatives and so on. Okay, so is this idea pretty clear? Yes.
So the reference point is wherever it's matching. So
The reference point is whatever you choose it kind of freely depending on your application.
So is it 0 for that?
So for us, yeah, so in this picture it's 0.
Okay.
In this expression it's generic W naught. Okay, so this is approximating J by a linear function in the neighborhood of W naught. All right, so sometimes we write gradients or slopes with a prime. So just note that this thing is just the slope of J at the point W naught, J prime. Okay, so this is what we have for the scalar case. Next, we'll move on to the vectors case, but it's important we understand the scalar case first. Vector case just kind of builds on it. Is there any questions on this scalar case? Is it making sense?
Is it just a tangent of that?
Yes, it's just the tangent at that point, exactly. Yep. Okay. All right, so let's now move to vector input functions. Again, the function is scalar output. It needs to be scalar output, otherwise we can't talk about any of this stuff. But it has a vector input. So we're going to fix a point, W naught. Now this is the vector W naught. And so if we want to talk about its elements, we'll write them as W01, W02, all the way up to W0D. Okay, that's how we talk about the elements of it. So how are we going to do the first order Taylor approximation now? Well, the only thing that changes from the previous slide is we have a sum over the different partial derivatives, and then we multiply them by the deviations from the reference, for each of the coefficients. So here we have a sum over J, where J is going across that vector, and then we look at the partial derivative with respect to Wj for all the different J, and we look at the deviation, Wj minus the reference at index J. Okay, so is it kind of clear how we went? All we did is we basically changed this term to a term where we have all the different W's and we have their sum. Okay, so not a huge leap. Any questions on this part? Okay, then let's talk about this part. So we're going to do something similar for this. Here we have a single W and we're squaring it. So over here, we have the norm, but remember what the norm is. I can write the norm as the sum over the different J of Wj minus W naught J squared. This is the 2 norm, the Euclidean norm. So you can see that this term also has that same form where you sum over the different components, but now you're just squaring them. Okay, so that's just a direct extension of this. And we have the order, the big O, as before. Okay, so this is how we do the Taylor series approximation when we have a vector-valued function. All right. Any questions on this? This is sort of like the main idea. Good with the main idea? Okay, the rest is notation, but as we'll see, it's kind of useful. So essentially what we want to do is often we just want to get rid of sums if we don't need them, because once you can move from a sum to a vector, it becomes more interpretable, becomes more compact. When you code it, usually it becomes more efficient. So how can we write this in terms of vectors? So the first thing is, this is just the jth component of our gradient vector. Right? So I'm going to write that here. This is our gradient vector, and then I'm going to use these square brackets sub j to say I'm extracting the jth component. Okay, so that's all we're doing here. Those are equal. Similarly, this is just the jth component of this difference in vectors, the original or the vector w minus the reference w naught. Right? If I look at the difference in vectors and then I look at the jth entry, I just get this. Everybody with me so far? Okay, so we have the sum of this entry of that vector times this entry of this vector, and hopefully you can recognize this as just what we call the inner product between those two vectors. So you take the first vector, transpose the second vector. That's all we're doing with this sum. Okay, so we have the gradient transpose the deviation. And now we have an expression with no sum. We just have the vectors everywhere, nice and clean, interpretable, and so on. And the very last step is let's turn this into an approximation. Let's do that by omitting this term. So we just have the first two, the scalar plus the linear term. And then for interpretability, there's one more step we can take, which is to recognize that, you might remember this from your basic linear algebra, that when you have just like A transpose B, let's say for vector A, vector B, this is what they call the inner product between those two vectors, at least in the case that we're talking about real valued vectors. So here I'm just rewriting it using this inner product notation with these angle braces. The inner product is basically a notion of angle from linear algebra. So in linear algebra, the norm of a vector tells us about how long it is. And if you're given two separate vectors and you want to know how aligned they are, the inner product gives you a way of computing that. And so this is just a measure of how aligned they are, essentially. What's really cool about this when you study linear algebra more deeply is that there's many, many different ways to build vectors. They're not just like tuples of numbers. You can actually think of matrices as vectors in the appropriate space. You can think about functions as vectors. And then you can talk about what is the angle between two functions. Well, once you know the inner product in that particular vector space, you can measure the angle between functions. So it's a nice way of handling a lot of stuff. So we're seeing this inner product for the first time, but we'll see that it comes back again, and we'll see that this kind of expression is going to be generic, whether we talk about vectors, scalars, matrices, or whatever. So that's why introducing this inner product idea. Now, the exact form of the inner product does depend on what kind of vectors we're dealing with. So here we're dealing with real valued vectors, and this is how it manifests as. If we were instead dealing with complex valued vectors, which definitely show up in ECE, then you would actually need to change this transpose to a Hermitian transpose, conjugate transpose. And that's how you would define the inner product for that vector space. So the exact form of the inner product depends on what kind of vectors you're working with. This is how it manifests for real valued vectors. Okay. So anyway, at the end of all this, this is our linear approximation, like this or like this, either way.
What's an example of a case where you see like a complex value?
Complex value, so communications has a lot of complex values show up there. A lot of medical imaging deals with complex values. So they often occur when you have signals that are modulated. So they exist at some like high frequencies and they exist around some center frequency, some carrier frequency. And typically you can't work with them at those high frequencies, so you bring them down to zero frequency. And once you bring them down to the origin, all of a sudden the spectrum is no longer symmetric. So what happens at negative frequencies is different than positive frequencies. And if you might remember from your signals and systems course, that means that the time domain function that gives that Fourier transform is actually complex value. So that's kind of the reason. So communications and a lot of applications, these vectors are just complex. Yeah, it's not something we don't deal with any complex vectors in this course, but since you asked the question. Okay, sure. Okay, so this is how we deal with vector input functions. We'll kind of do a little bit more with them on the next slide, but are there any questions at this point before we move on? Okay. All right, so let's try to understand again. We have been saying that the gradient tells us both the direction of maximum increase and the slope at the point we're evaluating it. So why is that? Can we prove this? So the answer is yes. So here's a nice picture of what's going on. So here's, this is like our cost J, and then this is just a case where we have a two-element vector, like A and B before. So maybe I can just write this as like W1 and W2. So the function we're dealing with is, at least a little piece of it is this like curved thing here. And here's, let's say, the reference point. This would be my vector W underbar naught. So that's my reference point in this two-dimensional space. And basically, if I look at what happens, the value, the height of the function at that point is the height of this line. Okay, so the length of that line, that's the height of the function. Now you might say, in what direction do I need to travel to maximally increase that function? So based on this picture, it seems like I need to move in this direction, and that's going to make me increase quickest. If I moved like in this direction, you can see like it's not increasing as much there. It seems to be increasing most along this direction here. So let's give this a name. On this slide, we're going to call the direction we're moving in U. And we're gonna just consider moving in an arbitrary direction U. So the U vector is not necessarily going to be aligned with the gradient. It's just some direction U. And in order to just think about it as a direction and not have length, we're gonna normalize. We're gonna make the norm of that vector U equal to 1. So now you can call it basically a direction vector. It's just a unit length vector that points in some direction, and that's the direction we want to look. Let's see what happens if we started our reference and we look in this direction. So this is how you define what's called the directional derivative at the point W0 in the direction U. So basically you're moving a tiny bit in this direction, and you're asking what's the difference in height between, here's my little step in the direction U, and you say, what's the height of the function there minus the height of the function back at the reference? And now if I've moved epsilon, I'm going to divide this difference by epsilon. That's basically how that's how we compute the gradient. You've definitely all seen this for scalar cases, and this is just how you can extend this to vector cases. You pick a direction, you move epsilon in that direction, you look at the rise over run. Does that make sense? Okay. So let's do some analysis of this function based on our gradient approximations. So the first thing is, let's take a look at this. So this is going to be our This is our W. We want to know what happens at this point W. And W is, in this case, W naught plus epsilon U. So that would mean that W minus W naught is going to be just epsilon U. Right? And the reason I care about W minus W naught is that that's the main thing over here. So I want to say the function at point W is approximately equal to the function at the reference plus the gradient transpose the difference, W minus W naught. So applying that down here, when I take this minus this, which is exactly what we have here, all I'm left with is this term. Right? And so that's what I have here. Actually, we're using this, we're including the order term here. So this, when I take JW minus JW naught, I'm left with this. And in particular, this is just epsilon U. So I get this transpose epsilon U, which is this, plus the order of the norm of epsilon U squared. And if you think about what is that, so what's the order of the norm of epsilon U squared? Well, one property of the norm is that if you scale the inside of the norm, then the outside of the norm scales by the same amount. So this would be, and because of the square, it's going to be epsilon squared times the norm of U squared. All right, so I pulled out the epsilon and then scaled on the outside. And then we said that this is just equal to 1 by definition. So finally, this equals order epsilon squared, which is where this is coming from. Okay, so in order to get from here to here, all I'm doing is I'm applying this equation from the previous page. So I have this. Any questions on that first step? Okay, so now we can do some simplifications. Okay, so let's look at the first term. So this is just a linear function of epsilon, and then we have epsilon on the bottom. So basically, this epsilon cancels this one out, and you'll just get this term over there. Does that make sense? This cancels this. Second, we have this other term. So this term, order of epsilon squared divided by epsilon, is just order epsilon. And what happens as epsilon goes to 0? So this is basically this directional derivative. We want to evaluate this for vanishingly small epsilon. We want to take a tiny step in U and see how much things increase. So we're really interested in what happens as epsilon goes to 0. Well, as epsilon goes to 0, this term this vanishes. Because it's order epsilon, and epsilon goes to 0, so that goes to 0. So that term vanishes, and all we're left with is this. Okay. So we have a nice, simple expression for the directional derivative if we, at this point, W naught. It's the gradient at that point transpose the direction we're looking at. Okay, everybody with me so far? Okay. Now the last thing, we're going to play a little bit of trickery to rewrite this in a way that brings a lot more meaning. So what I'm going to do is I'm going to multiply and divide by this term. So if I multiply and divide by the same thing, obviously that doesn't change anything. And I'm going to divide by the norm of U, which is like dividing by 1. So hopefully you agree that this equals this. But now we have stated things in a form that might be a little familiar to you. So this term could be familiar from the Koshy-Schwartz identity, which for generic vectors A and B basically says that this A transpose B divided by the norm of A and the norm of B is something that is from -1 to 1. It can never escape that range. And it says that the way to maximize this is to choose A and B that are collinear, meaning they're pointing in exactly the same direction. They can have different lengths, but the point is that they're pointing in the same direction. That's what it means to be collinear. So if you want to maximize this, you choose them collinear. So with that analysis, we can see, okay, if I want to maximize my directional derivative, that means I want to set this to 1, which means I want to take u collinear with the gradient. So I want u to be pointing in that direction of the gradient. Okay, so that's how we know that if you want to find the direction that maximizes your slope, it is the gradient. We just proved that. Okay, so that's, yeah, basically the maximum slope occurs in the direction of the gradient. Second is, well, what is the value of that maximizing slope? Well, that occurs when u is in the direction of the gradient, which makes this whole thing equal to 1, at which point this is the value of the slope. It's the norm of the gradient. So these little arrows, again, they tell us the length. Let's say we go back to this picture from the very beginning. This is in 2 dimensions. So each of these gradient vectors is a 2 by 1 vector. And the length of the arrow here is showing you the norm of that vector. So, for a reference point out here, the norm is not very big. For a reference point here, the norm is very big. And then you can see the direction of the gradient is the direction of the arrow. Okay, so that's essentially the proof of why the gradient tells us the direction of maximum increase as well as the maximum slope. Okay, and we were able to do this with that linear approximation. So this is the first time of several times we're going to use this to do some nice analysis. Okay, any questions on this page? Okay, so hopefully this tells us now, explains why the gradient is telling us the information it is. So let's say the last thing we'll talk about today is how to extend this to the matrix input case. So we talked about scalars, scalar input, vector input, now matrix input. So we have a matrix W, and let's denote the entries of the matrix W by the little w's, non-boldface, with indices ij. So in other words, I indexes across the rows, j indexes across the columns of W. And at the ith row and jth column, the entry is little wij. Okay, so we have a reference point, which is big W naught, and the first order Taylor approximation of j at W naught. Okay, before we do the approximation, let's do the exact equality. So it's again just a direct extension of the vector case. Here we have the constant term. Here we have the scalar valued partial derivatives. Now we have to take them over all the different entries, and we have a double sum over all those entries. And here we have the perturbations, again, the scalar perturbations. Right? So it's very much a generalization of the vector case.
So I actually have a question about the last slide.
Yeah.
If we can prove that like the gradient is what it is basically, why are we getting rid of the magnitude of the gradient? If we just took a step in the magnitude, would that not take us to the highest point already?
So the gradient changes. So can you see how like the gradient at this point is pointing in one direction, but at this point it's changed direction? So like maybe the minimum is over here, but if I'm here, I think that it's in this direction, but it's actually not.
Can you not just take a step in the length of that arrow though, or is the arrow like not the right?
So we can take many small steps and we can keep readjusting as we go. Is that?
Was there any reason why, like, unless the magnitude is just so big and I'm not understanding that, but like is that arrow what the magnitude of that gradient at that point is? Or is that just a random picture?
I mean, it's just a picture, but you could imagine that it is. I mean, I'm not sure what.
So like instead
you're
of
asking.
calculating and taking 10 steps to cover the distance of that one small arrow, why not just take the distance, like that arrow step?
Well, because it's pointing in the wrong direction. So like here, let's come back to here. So let's say that I wanted to end up over here, which is the minimum, and I'm right here. Well, the negative gradient is actually pointing there. Right? So if I'm here, I think, oh, I should go downhill. Well, I can't, let's see. Yeah, I think it is pointing up. So downhill at this point is pretty much that way. And that's obviously not going to bring me here in one jump, right? So I have to take many little steps, and as I take those steps, my gradient keeps changing, and eventually I will get around to the
You have
minimum.
to tell it how much to step. You have to say
Yes.
how much to step. It doesn't. Okay.
Yeah, so we'll get to that when we talk about the algorithm. But if you take too big of a step, you can actually get much farther away than where you started, right? So the key will be to take small enough steps. We'll be able to prove that works. Okay, so let's see. We're back to the matrix input case. So in this case, it's just like the vector case, but we have a double sum, and we have to consider all the different entries in the matrix. So that's what we have for the gradients. And then this part, if you remember the Frobenius norm, this is just a double sum. The Frobenius norm squared is a double sum over the entries squared. So that is, again, just a direct extension of the vector case as well. So otherwise, what we can do is we can try to get rid of these sums and rewrite things in terms of matrices. So for that, we just have to do a little bit of linear algebra, kind of bringing us back down to homework 0. So let's realize that this is just the ijth entry of W minus W naught. And this is the ijth entry of the gradient. But we actually want to swap I and j. So we want to swap I and j here. So I'm writing ji, and to do that, I can transpose the matrix. So the reason I'm doing that is that now let's consider this innermost sum. So now hopefully you can see that that is a matrix multiply. So we have this matrix here. This is our gradient matrix, and then we're indexing I across the columns. And we have a second matrix. We're indexing I down the rows over here. And with this sum, we're summing across that I. So essentially what this is this is the matrix multiplication of this matrix times this matrix. But now we're evaluating that at the jth row here and the jth row there. So in other words, we're doing a matrix multiply and evaluating it at position jj, jth row, jth column. And then we're summing over those j's. So this is where we have a form like this. Oops. So we do this matrix multiply, but then we're looking at the jth row and jth column of that matrix. So this is the matrix we're talking about. We're looking at the jth row and jth column, and we're summing over all j. So if you remember, that's what the trace is. The trace of a matrix is just the sum of its diagonal entries. So that's how we can rewrite this whole thing as the trace of this matrix product. And it turns out that that is the inner product for real valued matrices. So when you have a real valued matrix pair and you want to say, what's the angle between matrix A and matrix B? What's the inner product between them? Basically, it's the trace of A transpose B, or it almost is a little bit easier to interpret in terms of sums. It's like you're doing an element-wise product of A and B and then summing all the entries. So what we see at the end of the day is even for matrices, we have this same form as for vectors. J at W is J at the reference plus the inner product between the gradient and the perturbation. So it has exactly the same form. All that we change is the definition of the inner product. Okay, so that's good for today. We'll do an example working with this next Monday after the midterm. But good luck with your final midterm preparations. Come see me in office hours if you have any questions. And we'll see you on Friday.